Well, the greenhouse effect is really central to the whole story of the climate problem, so it's worth trying to understand it in a bit of detail. And there are an awful lot of people who have the strange idea that we don't really understand it. Some of them think the experts don't understand it. That's absolutely nonsense. The problem of Earth's radiation balance was first studied 150 years ago or more, and bit by bit the story's been put together. It's as solid as a rock. There's nothing controversial about it whatsoever. So this picture is something we've seen before. This shows the sun's energy entering the Earth system. It's the big fat yellow arrow. Some of it gets reflected, some's absorbed by the atmosphere, and the rest gets to the surface. And the fat red arrows are showing this situation where Earth's own radiation is delayed in the lower atmosphere in such a way that it circulates up and down and sideways before it eventually escapes at the top of the atmosphere to space, balancing the energy system. The greenhouse effect is often likened to laying a blanket over the Earth, and there's some justice in that analogy. This is roughly how a blanket works. So just imagine that Earth is radiating those little stubby pink arrows at the bottom, and when the heat reaches the bottom of the blanket, it's transferred to air molecules which are being trapped inside the spaces of the blanket and inhibited by those fibers, can't move as freely as they normally would. So the inside of the blanket contains air which is heated. Of course, it's not perfect, and near the top of the blanket the heated molecules escape, and away they go upwards, getting cooler as they go. That's how a blanket works. So if you think of the same thing in terms of individual photons, the photons from the sun, the ones that don't interfere with clouds, come straight down to the surface. The atmospheric gases hardly affect them at all, but Earth's own radiation, being in much longer wavelengths, just happens to be of a kind that does interact with the greenhouse gas molecules. And so those photons are dancing around in the bottom of the atmosphere, going up and down and sideways, and until eventually, by a process of transfer and random travel, they reach the top of the atmosphere and escape. This is the picture if we think of molecules instead. So the heat rises off the Earth's surface, and the population of greenhouse molecules is greatest near the bottom, so the chances of a collision are greatest. And so the photons make their way through this gauntlet, being retarded and energizing the lower atmosphere in the meantime, until they reach zones higher up where it's colder and the greenhouse gases are less abundant, and that's when they get their chance to escape. Now, you might be wondering why on earth it is that nitrogen and oxygen, which are far more abundant in the air than either water, which is typically something like 4%, and carbon dioxide, which is only much, much less than that, why these gases and not the others are responsible for the effect. And the answer is provided by physical theory. Only molecules with 3 or more atoms are capable of capturing an infrared photon. So here are the 4 most important ones: water vapor, carbon dioxide, methane, and ozone. And the photon enters the molecule in such a way that its vibration frequency is altered. So the molecule jumps around in a different way, and that can be translated to neighboring molecules, a bit like this on the right. So after capture by a photon, that water molecule jumps a bit more energetically and transfers its energy by collision with, say, a nitrogen molecule. Is much more likely to bump one of those than others, because they're most of them. And the second way it can behave is to get rid of its photon again, which it typically does in a fraction of a second, something like a thousandth of a second, although the time interval varies a great deal. So the molecules are taking up and releasing the energy that they gain by photon capture all the time. And just in case you think that Earth is unique in this respect, of course it's not. Other nearby planets, Mars and Venus, also have carbon dioxide in their atmospheres, although the situations are very, very interestingly different. Mars has a very tenuous atmosphere, only about 1% of the density of Earth, and of the gases that are there, most of it is carbon dioxide. But because the atmosphere is very thin, Mars is cold, and the carbon dioxide there only causes about 4 degrees of warming compared with 32 or so on Earth. Venus has the opposite situation. Long ago in the history of that planet, Venus seems to have begun to warm and then transferred all the carbon from its crust into the atmosphere. And today, as far as we know, all the carbon on Venus exists in the atmosphere. It's got about 250,000 times as much CO2 there in an atmosphere nearly 100 times denser than the Earth's, and as a consequence, the surface temperature there is about 460 degrees, entirely due to the massive greenhouse effect there.